All right, and now we're ready for question number 3. So on this video, we'll work through the third question on this assignment of moles, empirical formulas, molecular formulas, percent composition, some of those kind of things. We've gone through the previous two, and again, if you feel like you're ready to do this one on your own, do the whole problem, do part of it, check in with us, do the whole thing, and just jump to the very, very end. I'll have all the work on the screen as you've seen, and you can see if you've done it right. I will say on this one, the mole ratios that you'll get when you do the mole ratios between the elements come out a little bit funny. The last one they were nice and perfect whole numbers. This one they come out a little more complicated. So that's sort of why I've got it for the third question in this packet, and not the very first one, because the ratios are a little bit tougher. So don't let it intimidate you, but feel free, if you're feeling a little brave, to go ahead and do as much of this as you can, or even the whole thing. And if you get it right, you're gold. That's awesome. Okay, so let's take a look at the information they've given us. A new hydrocarbons have been synthesized in the lab. All right. A 0.7789 gram sample has been found to contain 37.20% carbon, 54.22% nitrogen, and the remainder is hydrogen. So now this one's only got 3 elements, but we've done something different on this problem compared to the last 2, and that is, instead of telling me how many grams of carbon, how many grams of nitrogen or hydrogen are in this compound sample, they're telling us by percent. And there's a little bit of a trick to that. You want to keep in mind what the word percent means. Percent literally means out of 100. In other words, if I had a 100 gram sample of this new hydrocarbon, as we're calling it here, then 37.20 grams out of that 100%, out of 100, 37.20 grams out of 100 would have been carbon, 54.22 grams out of 100 would have been nitrogen, and the rest would have been hydrogen. Now you can figure out what the rest is, right? It's not very much, and we'll be having to do that here in just a moment. But we don't have to use masses necessarily if we're giving percentages out of the gate. And you'll find out in a lot of these problems that they are giving them to us in percentages. We just have to do a little bit of a work out front to use those percentages to get the masses that we need to go ahead and figure out what our sample is going to be. Okay, so let's start out with that. Let's start out with the 0.7789 gram sample and figure out what is 37.20% of that. Okay, if that's what we're looking for here. 37.20%. Now we're going to want to write the percentages as decimals when I go punching them in my calculator. So this is 37.20% written here as a decimal. 37.20% written as a decimal. We don't want to use them as percentages because in a calculator the percentages doesn't really work. We use them as decimal form because the calculator knows how to handle that. And most of our calculators that we're used to using, they don't have a percent button. There are a lot of grade school sort of calculators, simple, sort of just basic 4-function calculators that might have a percent function as well. But we usually don't see a percent calculator on a non sort of store calculator. You have one that's more for business or accounting. We aren't going to have those here. So 37.20% is 0.3720. And that we need to take times our 0.7789 gram sample of compound. And that'll tell us how many grams of carbon there are in the compound. Okay? And then we know what to do with that. We've done that already. We're going to do that in just a moment, and we'll go ahead and work the math out. We also have 54.22%, which is written here as a decimal, of our sample, which is still 0.7789 grams. That's our nitrogen, so that'll tell us how many grams of nitrogen there are. And then the remaining percentage is the hydrogen. Now, how much is that? What is the remainder here? All right, well, let's quickly calculate that. I can take 100%. Oops, I think I might have shut off here. Yep, 100% minus 37.20% and minus 54.22%. And that'll tell me that the remaining 8.58% is my hydrogen mass. So 8.58% is 0.0858 times my original sample's mass as with the others, and that'll tell me how many grams of hydrogen are involved. Okay, now let's do those calculations and figure out how many grams we've got. We've got 0.3720 times our times our 0.7789, and that means out of that sample 0.2898 grams are carbon, right? And again, like I said in the last video, we're going to be working on a rounding and the rules of significant figures. But this 3720 has 4 measured values that we want to show in our next step. And so in my answer here, I've got 2898. Those are 4 measured values as well. All right, more on significant figures later on. The next calculation we want to do is that 54.22% for the nitrogen. So that's here, 0.5422 times, oh shoot, let me see here. Let's get back to where we were. There we go. Times our 0.7789 grams, and that's a little more than the carbon was because it's a larger percent. So 0.4223 grams of our sample is nitrogen. And then the remaining amount is our hydrogen. So there's 2 ways you could get this answer, right? I could go back over here and just take 0.7789 and subtract out these 2 values that we've just found, and that should give me the leftover hydrogen. Or I can take the percentage times my mass, like with the others here, and that should give me the same answer for the hydrogen. In fact, just to double check our math here, I'm going to show you both. You don't need to do both, okay? One way or the other, you're kind of basing your third answer here on the other 2. One way or the other. So however you do it is fine. It doesn't really matter. So 0.0858 times 0.7789 tells me that there's not a lot of hydrogen here. Looks like 0.0668 grams. And just to double check that we in fact have our 0.7789 gram sample, I'm going to go ahead and just punch these 3 numbers into my calculator and add them up. And just make sure that I in fact have accounted for all the mass in my sample. So 0.2898, oops, plus 0.4223 plus 0.0668. And there it tells me, yes, I've got 0.7789 grams. I've accounted for it all. It doesn't hurt to do that, because before you go on and do a bunch more math, check that you've got the math you've done so far correct, if there's a quick way to do that. Okay. Now, I'm a little crowded here, but I'm going to need to convert all of these into moles. Okay? So like we've already done, from here this problem looks a lot like the others you've already done. There are 12.01 grams of carbon in a mole. There are, oops, got a little ahead of myself. That's what happens when you're hasty. In a mole of nitrogen, there is 14.01 grams. In a mole of hydrogen, there will be 1.008 grams. And those are all masses off my periodic table that I've used in previous problems or just gotten so familiar with that I don't have to look them up. So until you get there, go ahead and look them up. You're always going to have that AP periodic table to rely on. This guy, shucks, where'd it go? This guy. So you'll always have this periodic table handy and available to you. Quizzes, tests, labs, anything you do. And so certainly don't feel like you have to memorize things. It's just a matter of speed. So let's punch this in and see what we get for our answers. 0.2898 divided by 12.01 is 0.02413 moles. 0.02413. Okay, for my nitrogen, I've got 0.4223, and that gives me 0.03014 moles of nitrogen. Okay, and then for the hydrogen, we've got 0.688 divided by 1, oops, 0.008, and that gives me 0.0683. We're going to give ourselves 3 digits on the hydrogen because its mass had 3 digits, because its percentages had 3 digits. Okay, so right now we've got our moles of everything, and again, like usual, we want to look at that now and say which one is the fewest, which one is the lowest quantity. My carbon is the least. Okay, my carbon is the smallest one, 0.02, 0.03, 0.06. So I'm going to divide all of them by that smallest one. In this case, we've only got 3 elements, so that saves us a little bit of trouble. But dividing this out by our carbon, dividing this out by our carbon on both of them, and be careful that you use the same number in the denominator no matter what. Okay, and then we're going to divide these out. Now, keep in mind, I mentioned at the beginning of the video, and I think in an earlier one too, that on this problem we get a little funnier ratios than we're used to. So let's punch in the calculator and see what I mean. 0.03014 divided by 0.02413. The calculator says 1.25. Remember, we can have this come out nicely to nice whole numbers, like in the last problem. We can have it come out to nice halves, even. In this case, it's coming out to 1.25. That's kind of ugly at first. But let's just go back to that here in just a second. We'll figure out what it means. 1.25 moles of nitrogen for every 1 mole of carbon. That's what that's saying. That's a ratio we haven't seen before, and it's a little gross when we're not used to it, but we'll have a solution for you in just a second. On the second one, 0.0683 divided by that same 0.02413. And this ratio, did I have a typo here? It's not what I had in my previous problem. I have a mistake here. I wonder if you guys have it too. It's right up here. I don't know if you see it on my calculator, but I punched this in as 688. It's supposed to be 668. That changes a little bit. So let me just fix that. And I bet some of you are thinking, what is he doing? And is he going to have to come back and fix it? Yes, I am. So that's why you use pencil or a digital screen. That lets you clean it up later. So 0.0663 instead, as I round that off. Let's try that again. 0.0663 divided by 0.02413, and that comes out to be a 2.75 to 1 ratio. Again, not real pretty, for being honest, but a 2.75 hydrogens for every 1 carbon. We can't write a ratio like this. Now I want to just show you what I mean. We've got carbon, we've got nitrogen, and we've got hydrogen here. C, N, and H. And we've got ratios of 1.25 nitrogens and 2.75 hydrogens for every 1 carbon. That's a ridiculous looking formula. You can't have that, right? We can't have fractions in our subscripts because you can't have 1.25 nitrogen atoms. That's impossible. So what do we do to fix this? You want to think about this a little bit like getting rid of improper fractions or mixed numbers or whatever you want to call these. But in any case, when you recognize that your subscripts here, or your ratios, which is where those come from, right? When these are in quarters, 1.25, that's 1 1/4, right? And when you see 2.75, that's 2 3/4. That means that these ratios are in fourths right now. And we want to get rid of the fourths. So when this is in, these are ratios of these subscripts that are in fourths, units of quarters, okay? We want to take this whole thing here, basically, to get this to whole numbers, which is what we have to have for it to be a proper empirical formula. We need to take that whole thing times 4, okay? Because we want to get rid of fourths. 4 cancels out the 4 in that denominator, and we'll have nice whole numbers that are simplified. And you'll see what I mean here in just a moment. So let's go ahead and take our formula, take the whole thing times 4. Well, C1 times 4, I can do that one, is 4. But let's see, N, 1.25 times 4. Now some of you I know will just do this in your head, but let's just take our time here and show it. 1.25 times 4 is 5. So that's a 5 in my nitrogen. And then 2.75 times 4, that's my last one. Maybe that one's not as familiar to you, I don't know. 2.75 times 4 gives us an 11. Okay, now that means we've got H11. Now 4 to 5 to 11 is whole numbers. 4 to 5 to 11 is simplified down. You can't simplify it any further because you have 2 odds in there and you can't reduce those. So this is an appropriate empirical formula. And I can go ahead and label it as such. Now here's the deal. Keep in mind that ratio that we didn't like here a moment ago, the 1 to 1.25 to 2.75 ratio, it's still there, right? We just took everything times 4 to get it to whole numbers because an empirical formula has to be in whole numbers, simplest whole number ratio, all right? Now, at this point, we've gone through question A in more or less the same way that we've done the others with a few little oddities in there. We had percentages to deal with, and we had some bigger, funkier ratios to deal with in fourths, but everything else is pretty much the same. Question B, in fact, does it the same way again like the others. It says, figure out that molecular formula. So we're going to do it the same way we've been doing it with the others. I'm going to give myself a little more space again. And if its molar mass is found to be 646, all right, so I'm going to switch the colors again. Remember, we want to take molar mass, 646 grams per mole, divided by the mass of the bugger we just calculated. That C4N5H11. We want to figure out what the mass of that is and put it here in the bottom. And that'll help us to get our multiplier, right? So go back to my calculator, and I need 4 carbons, C4, so 4 times 12.01. Plus, I need, let's see, 5 nitrogens. So 5 times 14.01, that's my nitrogen mass. Plus, I need 11 hydrogens. That's 1.008 for a grand total of 129.2. 129.2. Now again, as usual, fingers crossed, if I do my division, this should come out to some nice whole number multiplier. And perhaps, again, you're a math in your head type. That's awesome. I like to do that too. But for the purposes of those folks following along at home who maybe don't math in their head, whoa, that's perfect. That's a 5. It's a 5 multiplier. So I'm going to take this whole thing times 5 to get to C20, that's pretty big, N25, H55. Boom. Okay. C20, N25, H55. And I'm pretty sure I know that what the formula is on that. I'm pretty sure that's the empirical formula, the molecular formula rather, for a pretty well-known blood sugar medication called Metformin that kind of helps with controlling blood sugar and so forth. And anyways, I'm pretty sure that's where I got that from, if I think back right. So I've taken my C4N5H11 times 5 and got C20 N25 H55. Those are pretty big numbers. And if you looked at them at first glance, you'd probably very easily recognize that they're all multiples of 5. Well, that's because you're seeing the multiplier that we did sort of in reverse, right? If I was going backwards and said, what's the empirical formula for metformin? If its formula is C20, N25, H55, you might go to that and say, well, I can reduce that by a factor of 5, and you'd get right back where we started with our empirical formula. So there you go. Now, I want to mention briefly now, and I'll be talking about these later on when the year starts, that this is a precursor to what we call combustion analysis problems. You won't always have percentages or masses of the different elements just given to you and say, oh, go convert these to moles and do mole ratios and figure out the formulas. Eventually, we're not going to get those masses for just carbon. We're going to get a mass of carbon dioxide gas that was produced. Or we won't get a mass of hydrogen. We'll get a mass or volume of water vapor that was produced, or something like that. And you'll have to do a little bit more with that. So this is really a precursor to what's called combustion analysis. And frankly, empirical formulas and molecular formulas are things that we do in first-year chemistry a fair amount. And students usually have a pretty good grip on. If you feel like you have a really good handle on these right now, after these first 3, you're in business. Okay? You're in great shape. You've mastered as much as we want you to take from first-year chemistry, and maybe even just a little bit more with some of these tougher ratios. When we come back to the beginning of the school year and we work on stoichiometry as our first main unit of the year, you're going to find that combustion analysis is built off of these problems right here. And taking a compound apart and studying its parts to figure out what its structure and its formula were in the first place. So empirical formula has a purpose that we build on later on. It will not be part of the summer assignment at this point, but it will be part of September. So can't wait to go through those with you. They're a lot of fun. Challenging, and they look really big and intimidating, but when you figure them out, they're pretty simple because you're super smart. And we'll talk to you then.